want to start by giving kind of like an overview of the course. So there are 6 lectures to this course. Um, Last week we talked about introduction to blockchain, and today we're going to talk about cryptography. In the future, we're going to talk about Bitcoin, Ethereum, and then some limits and ways to attack blockchain, and then finally some of the applications of a blockchain. So there are mainly 3 sort of parts to the course. First part is the lectures. So typically there's gonna be like 30 minutes of lectures and then some time for Q&A, and then sometimes we'll have a small group discussion depending on the participation. And then some homework if you would like. If you have some extra time, it's mostly less than an hour to work, so you could do it if you want. And then some workshops. We're gonna have a coding session soon, and then some industry speaker coming over to give some talks. And then there's this component about final presentation. You can choose between doing some existing application research or come up with a new way of utilizing blockchain. This is entirely optional, and you don't have to do it if you don't want to. Um, So here's kind of the checklist to the course. You have 6 lectures. You have, you know, a couple workshops, some of which are optional, and then you have some homework that will help you learn better. So here's your timeline. So we are at week 2 right now, October 10, and then this is gonna go all the way to November 14th. So yeah. So that's it for the kind of overview of the course. And next, I want to jump into what we're going to talk about today, which is cryptography. Let's see. All right, yeah. So the goal for today's lecture is for you to kind of understand the magic behind why blockchain work. And to do that, we're going to talk about a couple of things. First thing is hash functions, and then the second thing is encryption. So there's 2 types of encryption. There's symmetric and asymmetric. We're going to talk about each one of them. And then there's digital signature. We're going to talk about how cryptography is used in blockchain. And then lastly, we're going to kind of go over some of the concept of zero knowledge proof. So first, cryptographic hash function. So what I want to start by talking about what is a function. So I think most of you learned it in algebra class. It's basically something that takes an input and then produces an output, right? So for example, f of x equal 5x. If the input x equal 1, then the output would be 5. If the input x equal 2, then the output would be 10, right? Um, so then what is a hash function? Well, the basic idea is the same, right? You have an input, and this input sort of go through some mathematical transformation, right? And then produces the output on the other side. So some of the things to note for hash function is that the input right here could be any size, so any arbitrary size. Some people also call the input message, just to keep that in mind. And then also for the output, it's the same size. So you have the input and it goes through this hash function and produce output. And something to note for the output is the output is the same size, regardless of the size of the input. So, and some people call the output digest or hash, basically the same thing. So here's kind of example of a hash function. You have, let's say your input is Fox, goes through the hash function, and then the hash output will be something random like this. And let's say your input is this sentence, goes through the hash function, produces a different output. Even if you change a word, so from runs to walks here, go through the same function, produce a different output. So some of the properties, the key properties of hash functions is deterministic, meaning that the same input produces the same output. And then the second thing is collision free, meaning some people call it collision resistant, meaning that different input will have different output. Well, this is practically true, but not theoretically true. We can get into that more in the future, but it's basically hard to find one that is not collision free. So, and then the next sort of property is hiding. So, meaning that hash function is a one-way function. So, given an input, given an output, is infeasible. It's very unlikely that you could find the input. And then next is puzzle friendly, which means that you are given the whole output and part of the input, but it's still difficult to find the input. It's more possible than the hiding property, but it's still difficult to do. So next is computationally efficient, meaning that it doesn't require too much computational power to compute the hash function. So an algorithm used for hash function is called SHA-256. It's part of the bigger family called SHA-2. It's basically the 256 means its output size is 256 bits. And this is the algorithm that's used in Bitcoin along with some others to do a hash function. So next, for the encryption part, like I said, there are two parts, symmetric and asymmetric. So we're going to start by talking about symmetric. So symmetric encryption. So for symmetric, basically mean that you use the same key for both encryption and decryption. And something to note is that we'll go over an example in the next slide, but something to note is that the security of this kind of encryption method depends on you keeping the key safe, right? Nobody else can access the key. So here's an kind of example. So you have this sort of table right here. So like a mapping table, and then A maps to N becomes A, and then B becomes O becomes B, something, and so on, right? So now you have a message that you want to encrypt. So let's say hello, and then you encrypt it using this table. So H now becomes U, E become R, L become Y, O become B. All right. So this is the message that you want to encrypt, and this is the encrypted message. So now, let's say we have three people, Alice, Christopher, and Bob, right? And the key here is the mapping table that we talked about in the last slide. So right here, and only Alice and Bob, they have the key. So now Alice wants to send a message, let's say hello to Bob. So Alice uses the key to encrypt hello to this thing URYYB and sends that URYYB over to Bob, right? And because of Bob also have the key, the table, so he's able to decrypt the message back to hello, right? But now if Christopher right here wants to intercept the message, and all he gets is the encrypted message, so URYYB, and he doesn't know what that means, right? Because he doesn't have the key. So this is a kind of example of symmetric encryption. So next, for asymmetric encryption, this is kind of another way to encrypt messages. So in this case, there are two keys. So each person have two keys. One is called public key, and one is called private key. And these two keys are kind of mathematically related to each other. And so it's actually that you use the private key to generate your public key, right? And then your public key right here is accessible to everyone, so everyone can have it. You can share it with anyone, but the private key, you can only keep it to yourself. Nobody else can know. So the more important thing here is the following. So this part, if you use the public key to encrypt, that means you can only use the private key to decrypt, and vice versa, right? If you use the private key to encrypt, then you can only use the public key to decrypt. So yeah, we'll go over another example in the next couple of slides, but now the security kind of depends upon you keeping your own private key safe, right? So if people want to send you a message to you, then they will use your private key to encrypt the message. And since only you have access to your private key, only you can decrypt the message. So as long as you keep your private key safe, then only you can see the message that were sent to you. So here's an example. Here's Alice, Christopher, and Bob again. So they each have a pair of public and private key. Again, they want to keep the private key to themselves, and then they could share the public key to anyone. So now Alice wanted to use Bob's public key to encrypt the message hello, right? Now the message becomes something unrecognizable, random strings or something, and she sends this encrypted message to Bob. Now Bob could use his private key to decrypt the message. So like this, so that goes back to hello. And now Christopher here, although he could kind of intercept the message and get the encrypted message, but he couldn't decrypt it because he doesn't have access to Bob's private key. He only have access to Bob's public key. So that's the idea of asymmetric encryption. You have two keys versus one key in symmetric encryption. So there's this thing called elliptic curve digital signature algorithm. It's basically like an algorithm to generate private and public key that's used in Bitcoin. We're not going to go into detail about it, but just something to know. And here's the next thing we're going to talk about is digital signature. So what is a digital signature? Well, it's kind of your signature in a digital way, right? It's used to prove that you own something, that you said something, to prove that something is from you or something belongs to you. So to basically to prove your identity. So think of it like applications of asymmetric encryption. So what you have right here is, again, Alice is trying to send a message, hello Bob, to Bob, right? And then Alice uses her private key to sign the message that produces a sort of signed message or encrypted message, right? And then send it over to Bob. Now Bob, using Alice's public key, is able to verify that the message that's sent is in fact from Alice and not somebody else. He actually needs also the original message and compare this one with that to see if the message was changed or not. But we'll talk about that later. So to kind of generate a digital signature, you need the private key and the message. And to verify a digital signature, you need the public key, the message, and then the digital signature, which is the signed message, the encrypted message. And you could kind of imagine in the case of Bitcoin, well, how do you know if someone is sending their own Bitcoin? Because this message right here equals the transaction. So you need to sign your own transaction using this method to prove that you own the Bitcoin that you're trying to spend, which we'll get into more next week or the week after that on Bitcoin. So just to kind of go over it one more time, Alice again has a key pair, private and public key pair, and then the private key is used to sign the message, and the public key is used for others to verify the message. And then she kind of signed the message with her private key, And then she published the original message, her public key, and then the signed message. And now on the other side, Bob now could use Alice's public key to verify the message that was sent from Alice. That's the kind of basic idea of digital signature. So yeah, the next part I want to talk about, let's see, how cryptography is used in blockchain exactly, right? We kind of talk about some of the key concept here, but how exactly is it used in blockchain? So if you remember from last week, we kind of go over the example, but I'm going to go over it one more time. So you have some data and you put those data in a block, you feed those blocks into a magical box, and then this magical box will produce a unique fingerprint that kind of like the ID for the block, right? And you can probably guess this block right here is just a hash function. You have some data that's feed into this hash function that produce a unique output. So the output of hash function become kind of the fingerprint of the block. So now you have this thing right here. And then next you have some more data. You put those data into a block. And then the way to connect those two blocks is to put the fingerprint of the first block inside the second block. So like this. Well, why do we do this? Because now, why does this link the block together? Because now if we hash this whole block into this hash function and produce a unique output, now this output is dependent on the data inside. So it's dependent on the fingerprint right here. So if someone were to go and change this data, or some data right here, hope you can see the drawing, but if somebody were to change the data inside block one, now the fingerprint for block one changes, and now this doesn't match. We'll kind of go over example in just a minute here, but that's kind of the key idea. And then again, you have some more data. You link those by putting the fingerprint of the previous block to the next block, and then so on and so on. That's what's mean by blockchain, right? So again, the magical box right here is the hash function basically. So we're gonna have some demo, which is a really cool one. Let me see. Well, I think it's a cool one. Okay, so we talk about SHA-256. So this is a sort of like a visual demo of it. So you have some data, you can type anything into it, and the following right here is a hash. So it's the hash of the 256 bits, but it's represented in hexadecimal form. So that's why you see the digit from A to F, well, 0 to 9 and A to F. You could type anything, and then the hash will be different, right? So let's see, hello, and then that produces that. But any slight changes to the data inputted. So hello 1, notice the hash changes, right? But if we go back to hello, then it's the same hash that we see before. I'll include this website in one of the homework assignments so you can play around with it. And next, now we have a block. So you basically have some data. You have the block number, you have the nonce. Don't worry about these two parts. We're going to talk about that next week. But the basic idea right here is the hash is the output of the hash right here is putting everything, the block, the nonce, the data, and then hash to produce it. So again, you have hello, and then you have, if you change even the block number, the hash changes. If you change the nonce, the block, the hash changes. So everything inside this block is could change the hash. So what does it mean to have a blockchain, right? Let's say, so this is a perfect blockchain right here. Everything is green, everything is fine. everything's kind of verified, everything is good. But if you go ahead and change, let's see, the data inside block 3, so you change it. So now everything that kind of goes beyond block 3, it kind of goes to red because the hash doesn't match anymore. Hopefully I'm making sense, but you can see the hash right here. You can see the arrows. So the hash of block 3 matches the hash right here, right? The hash of previous block, the previous hash of block 4. So this hash is the same as this hash right here. So if you change anything inside block 3, the hash of block 3 changes. So, and now this has been changed and something is wrong. And to go kind of one step further, the key idea of blockchain is giving sort of everyone a copy of the data. So you don't only have one person who have possession of data, everyone kind of have part of the whole copy of the data. So these three are identical. And now you can imagine if someone is being malicious and trying to change some data here. And even though this block goes to red, the other two people will be able to tell that the blocks is different, right? So that's the basic idea. And to kind of give you more idea, we'll go over this again the next time we talk about Bitcoin. But the data right here in Bitcoin, the data part, right? The data part that we talk about is basically transaction. So we record the record of transaction. So the data could just be replacement transaction, and then you can say, some amount of money was sent from who to who. And that's kind of the key idea for Bitcoin. Okay, let's go back to the slide. So yeah, that's kind of the demo that you can play around with if you would like. But we'll go over it one more time the next time we talk about Bitcoin. So next, I want to talk about zero knowledge of proof, which is kind of a magical thing, right? The idea is you're trying to prove that you know a secret without revealing the secret. So it's kind of like providing companies with the data they need without revealing the data itself. So proving something is true without revealing the thing that we're proving. It's kind of like a novel idea, but we'll have some more material on this. I don't want to go over too deep about this just because next week we're actually going to have a workshop about this. But it isn't actually 100% proof. You're trying to kind of minimize the probability that someone is lying to you. So you do some kind of operation over and over again or do something else, which brings me to the workshop that we're going to have next week, where we're going to dive deep into kind of zero knowledge proof with Fendora. It's a startup that's doing kind of financial blockchain on zero knowledge proof. So, do you have any questions or anything? Here's the kind of the homework. Again, here's the demo that I did. There's a video on this. So there's part 1 and part 2. And then here's the demo, the link to the website, and then some other material that I think could help you understand more about what we talked about today. And as I promised, some more material on zero knowledge proof. Fascinating stuff. You can take a look at these if you would like. So yeah, that's it for this lecture, guys. Thanks for joining. Any questions, just let me know. Otherwise, I'll see you next week during the workshop. Thanks, guys.